to make a smooth transition here. The subject of soil structure interaction, which is certainly an important one in geotechnical earthquake engineering. A lot of what we do is motivated by the desire to design a new structure to be earthquake resistant or to evaluate the earthquake resistance of an existing structure. And that structure may be a building, it might be a bridge, it could be a buried pipeline. We'll see that structural elements are going to interact with soils in a way that can strongly influence their behavior. So this soil structure interaction is really quite a complicated topic. It can become very complicated. And what I'd like to do this morning is to present some of the basic concepts to you and try to develop an understanding of when it's important and when it's not important. Because it's not always important for different types of structures and different types of soils. And then because it's an important part of foundation design, we'll go into a little more detail about the way deep foundations, piles and shafts interact with soils during earthquakes. So we often analyze structures, or we look at structures in our first introduction to structural dynamics by looking at fixed base structures, a structure that is rigidly attached to the ground. And so at the base of the structure, we can't have any displacement relative to the ground, we can't have any rotation relative to the ground. So it simulates the conditions we would have for structures that are founded on rock. But when we have structures that are founded on soil, now the soil is not rigid. The soil can be pretty compliant, pretty flexible, and consequently the base can move in addition to the structure responding dynamically. And so in situations like this, we'll often talk about a free field motion, that is a ground motion that's far enough away from a structure to not be affected by the presence of the structure and its response. But we'll talk about a foundation input motion as the motion that actually occurs at the base of the structure. And these two motions are not the same. So we'd like to know how the motion at the base of the structure, this foundation input motion, differs from the free field motion. Because that foundation input motion is what we should be applying at the base of our structure, our structural analysis. So the response of the soil is going to affect the response of the structure. The response of the structure is going to influence the response of the soil. So this is what we refer to as soil structure interaction. And we'll divide it into two components. Kinematic interaction that results from the stiffness of the foundation system. And the stiffness of a foundation prevents it from deforming in exactly the same way as the free field soil would deform. Now, if we had an extremely flexible foundation system, it would move with the soil, and its motion would be the same as the soil motion. But if our foundation has stiffness, even if it doesn't have any mass, it's going to respond differently. We'll contrast that with inertial interaction, which is the interaction that comes from the inertial forces that a structure will impose on the soil and on the soil's foundation. So we'll look first at kinematic interaction, and it has three main causes that we often talk about. One can be described as base slab averaging that results from the stiffness of the foundation system. The next is embedment. We know that ground motions vary with depth, and so a foundation that extends down below the ground surface is going to be subjected to a complicated loading history. And then there's wave scattering, which is a less significant effect, but we'll talk about it very briefly. So we might have, in the absence of any structure or any foundation, we might have ground movements that look like this. If we put a foundation on top of it, and that foundation has some stiffness, it's not going to move the same way. If it's rigid, it's certainly not going to move the same way. It can't bend like the ground surface is bending with these vertical displacements that are illustrated here. And so base slab averaging results from this foundation having having some stiffness that's going to keep it from moving the same way as the free field will. And this exists even if we have a foundation with no mass. A stiffness but no mass, and it's bonded to the soil, it can't move the same way the soil is moving. Embedment effects result from the fact that ground motion amplitudes vary with depth. And the phase also varies with depth because it takes some time for the ground motions to move up to the ground surface. So if we have a foundation that extends down to some depth, it's going to be influenced by vertical motions and their variation of depth, but also by horizontal motions and their variation of depth. And it's not hard to imagine that this effect should be related to the wavelength of the ground motions and the relationship between that wavelength and the depth of the foundation system. If we have very high frequency motions with very short wavelengths, which is kind of illustrated here, there's going to be places on the foundation where it's being pushed to the left and places where it's being pushed to the right. If we have a short wavelength, there will be a whole bunch of these forces, and they'll tend to cancel each other out. And we won't see much rotation or much necessarily displacement of the foundation. But if we had a wavelength that was the same as the depth of the foundation, then we're going to have perhaps forces pushing in one direction in the upper half of the foundation, pushing the opposite direction on the lower half of the foundation. It's going to make our foundation rock to one side. And as soon as the loads are dynamic, it's going to rock back and forth. And so we'll see rocking of foundations at certain frequencies, certain wavelengths, and only translational movement at other frequencies. Wave scattering results from waves that come up and hit the foundation and get scattered, reflected off in different directions at the corners and edges of the foundation. It usually has an effect on very high frequency components of motion, and often those frequencies are greater than the frequencies that we're really interested in. But it can be important in some situations. If we have deep foundations, say with flexible piles, piles just going to move with the soil. There would be high curvatures in the piles, but in many moments won't be large because the flexural stiffness, EI, is going to be low. So the deformation matches the free field deformation, the surface motion will be equal to the free field motion, and there won't be any rotation up at the surface. If we have a rigid pile in this soil, then all I can do is translate or rotate, and it's going to move differently than the soil moves. The surface motion is not going to be the same as the free field motion at the ground surface, and we can have both rotation and displacement up at the ground surface. And so if we have a pile-supported building at the top of this pile, we have to input rotation as well as translational movements at the base of our structure. The inertial interaction comes from the fact that the soil isn't rigid, it's flexible. And so when the loads are applied to the foundation, it's going to move. It can translate in 3 different directions, and it can rotate about 3 different axes. And the resistance to that, those kinds of movements and rotations come from the stiffness of the soil and the foundation. So we have 3 components of force and 3 moments, and they produce 3 displacements and 3 rotations. We can have a 6x6 stiffness matrix that relates the deformations to these forces that are imposed on our foundation system. Often we'll look at it in a 2-dimensional sense, in which case now we only have 2 displacements, horizontal and vertical, and rocking about 1 axis, and so the problem becomes simpler, or at least calculations become faster when we just have a 3x3 stiffness matrix. When our foundation moves through these forces that are applied to it, waves are going to be transmitted into the soil, and if we don't have any layer boundaries close to the foundation, they're just going to propagate away from the foundation. And so some of the elastic energy of this oscillating structure as it moves back and forth is going to go into the ground, and it's going to radiate out away from the foundation, and it's not going to be reflected back. So radiation damping tends to remove energy from our structure, so it can be a beneficial thing. When we analyze soil structure interaction, ideally we would do a complete analysis of which we would model the structure at a high level of detail, non-linear inelastic response of the structure, all of its components, the columns, the beams, the connections, any bracing systems, and we'd have a high-level model of our soil. We'd model the non-linear inelastic behavior of the soil, pore pressure development if we have soils that are going to build up pore pressures. We don't have very many tools that allow us to do this, though. A lot of the computer programs that we develop, we have some very nice geotechnical computer programs that model the soil very well in a great amount of detail, and the structure is modeled as a single degree of freedom system, or a very simple structural system. The structural models can model the structural behavior, different materials in great detail, non-linear inelastic, buckling, joint rotation, things of that nature, and they model the soil with springs. So there aren't too many programs that can solve the whole problem together. But there are some, and they're becoming increasingly available. So what's most commonly used is a substructure approach, where we separate the two problems. And when we use this approach, we'll use typically a geotechnical program to evaluate the kinematic interaction problem and calculate our foundation input motions, and then we'll use a structural engineering program to evaluate inertial soil structure interaction. And we'll do this in such a way that we can add the two responses together using the principle of superposition. So there's an inherent assumption of linearity here. But if we have a linear system, we can get an exact solution this way. So it allows us to use the codes that are available to us and that we are accustomed to using. We have typically geotechnical engineers solving part of the problem and structural engineers solving the other part of the problem. And it's really important for them to talk to each other, to communicate and make sure that each team understands what the other team is doing, so that there's no mismatches or conflicts between the two analyses. So if we analyze kinematic soil structure interaction, we're going to be looking at the effect of the stiffness of the foundation system on the foundation input motions. So we'll typically analyze it with our foundation system in place. It will have stiffness, but it's not going to have mass. We'll model it as a massless foundation system. And we'll perform a finite element analysis, finite difference analysis, and we'll calculate the motions at the top of our foundation system. So we'll have say a horizontal displacement, a rocking turn that may occur. We can do this in 1, 2, or 3 dimensions and calculate all 6 components if we need to. It's going to be, these motions are going to be affected by the geometry of the problem, about the response of all of our soil layers. It's going to be affected by the geometry of our foundation system and its stiffness. But the mass isn't coming into play here. We'll handle the mass in the inertial interaction analysis. Before that inertial interaction analysis, we develop impedance functions. I'm using impedance here in a different context than we talked about the specific impedance in wave propagation problems. That was the product of the density of the material and the wave propagation velocity. We're going to represent our soil by a Kelvin-Voigt model here. That's a spring and a dashpot in parallel. And so if we look at the vertical direction and apply some oscillating load, we can come up with spring constants and dashpot coefficients that will match quite accurately the response of an infinite half space here. And we can combine them by taking the stiffness and adding I times our dashpot coefficient times frequency to get a total resistance. That's the sum of the resistance provided by the spring and the resistance provided by the dashpot. So the spring resistance is proportional to the displacement. The dashpot resistance is proportional to the velocity, so that's where the frequency term comes in. And this I makes it complex, but it accounts for the phase difference, the 90-degree phase difference between the stiffness and the velocity, the displacement and the velocity. So this is what we could refer to as an impedance in the context of foundation design. So we can do the same thing for horizontal displacements and the same thing for rotational displacements, and by means of these springs and dash plots, have a good approximation of the way a half space, a flexible half space, would behave. So we can end up with a 6x6 matrix of impedance coefficients that have a real part and an imaginary part. And the real part handles the stiffness, the imaginary part handles the damping. If we attach that to our foundation system, and now we include the mass in the foundation system, we can apply our foundation input motion, a horizontal foundation input motion, to the end of this element. We can apply a rotational foundation input motion to the end of this rotational element, and I haven't shown it here, but if we're looking at vertical loads, we apply our foundation input vertical motion to the ends of this elements and calculate the response. If that response, if we're assuming linearity, that response will be accurate. It will be the same as we got from if we perform the complete analysis. Because the soil is not linear and structural elements at high levels of shaking may not be linear, we often use an equivalent linear approach where we're going to repeatedly analyze the problem and adjust our soil properties and adjust the structural properties to be consistent with the level of deformations that develop. But this is one of the ways that we commonly handle soil structure interaction. Now, we can ask ourselves, when is this important? When do we need to worry about it and when don't we? Again, our simplest case is a fixed base structure. We can imagine that we have a single degree of freedom system mounted on this little cart here, and it's attached to the cart by a horizontal translation spring and a rotational spring. And if these springs were infinitely stiff, then we'd have a fixed base system. It wouldn't be able to move horizontally at the base, and it wouldn't be able to rotate at the base. But if we allow these to have some stiffness that reflects the compliance of the soil beneath the foundation, then we can have some displacement and we can have some rotation. If we look at the mass up at the top, its displacement is going to be the sum of the displacement of the ground and the displacement of the base of the foundation. There will be a displacement that's due to the rotation of the base. It will simply be the height of the structure multiplied by the angle of rotation of the base. And there will be some displacement that comes from the distortion of the structure, the bending of this column that's holding up the mass. So there's 4 different components of displacement. The one that really places a demand on the structure is this last one here. That is the deflection of the structure that's producing forces in the structure. If we can go through and calculate the natural period of this system that allows compliance of the base, and if we do that, we can call that system natural period T tilde, and we can relate that to the fixed base natural period of the structure by itself. And if these two springs, the horizontal translation and rotation of the base, are infinitely stiff, then these two terms are infinite, and these two ratios go to 0. So our fixed base frequency would be the same as the frequency of our system. But if these terms are not infinite, if this foundation has some compliance, so it can move at its base and it can rotate about its base, then these terms will be greater than 0, which means that the natural period of our system is going to be greater than the fixed base natural period of the structure. So one of the important effects of soil structure interaction is to have a lengthening of the natural period of our soil structure system compared to just the natural period of the structure by itself. We'll also find, and we can show, that we get increased damping when we allow displacement and rotation of our foundation system. As that foundation system translates horizontally and rocks, it's going to be putting energy down into the soil underneath it, and that's going to radiate out and away. And so we'll have this radiation damping accounted for that way. So when Soil structure interaction is important. We see a lengthening of the natural period of our system, and we see an increase in the damping. So when is it important? If we look at a single degree of freedom structure on a circular footing that has some radius, we can look at this period lengthening ratio, and what we'll find is that its significance depends on the stiffness of our soil, vis a vis, and the natural period, or affected by the stiffness of the structure, and by the height of the structure. If this ratio is low, it means we have a stiff soil with a flexible structure on it. And we can see that the period lengthening is very small under these conditions. The ratio is just about equal to 1. If we have a stiff structure on a flexible soil, a soft soil, then this ratio becomes higher, and we start to see this significant lengthening of the natural period of our system. And we know the natural period of the system is important because it's going to influence how this system interacts with the input motions. And so soil structure interaction is important when we have stiff structures sitting on soft soils. They're small, the effects are small when we have a flexible structure on a stiff site. So if you have a very tall structure, a high-rise building that's on stiff soils, soil structure interaction is probably not going to be very significant. It's when you have a stiff structure sitting on soft soils that it is important. This notion of soil structure interaction and its effects came out of work that was done on nuclear power plants back in the 1960s or so, where you have these very stiff structures that have very thick walls for shielding of radiation, constructed in some cases on soils that had some flexibility to them. And so these effects became important there. So we see period lengthening being important if we look at damping, stiff soil and a flexible structure. The additional damping that we get from soil structure interaction is negligible. If we have a stiff structure on soft soil, it can become quite significant. So again, radiation damping is negligible when we have a soft structure on stiff soils. The forces going into the soil will not be that strong. But as our structure becomes stiffer or the soil becomes softer, it becomes more important. So it's important to recognize this kind of general concept of the relative stiffness of the structure and the stiffness of the soil as controlling when soil structure interaction is important. And it's important to recognize that when it is important, we see a lengthening of the natural period of our system, and we see an increase in damping. If we look at, so these are the effects that we see. We can find that soil structure interaction will decrease the demands on our structure under certain conditions, but not under all conditions. We'll find that it will often increase the total amount of displacement that occurs because we're having some additional means for deformations to occur. If our foundation is allowed to move, and if it's allowed to rotate, we're typically going to see larger displacements, total displacements up at the surface. This can be important when we have buildings that are closely spaced. In a number of areas, we have maybe an area where there are tall buildings, and maybe there's half a meter separation between the buildings. You see that in some U.S. cities. I don't know the extent to which it's true here. But if the buildings have different heights or different systems that respond differently, they're going to go back and forth, and that half-meter gap that exists may close because they're responding differently. And there have been many instances where buildings have collided with each other and caused a lot of damage due to what the structural engineers call pounding. Usually if there's a tall building and a short building, the tall building gets damaged where the top of the short building comes in and hits it. Maybe it's waist level, and it can cause a lot of damage. So that's another important factor to consider when you're looking at soil structure interaction. So soil structure interaction is not significant for cases where we have flexible structures on stiff soils. It can be significant for stiff structures on soft soils. The fundamental period of a soil structure system will be longer than the fundamental period of a fixed base system. That's an important effect. The damping of a soil structure system will be higher than the damping of the structure itself, because now we have soil damping and radiation damping coming into play, which don't exist in a fixed-base system. And the total displacements can be increased by soil structure interaction, which can be important when we have closely spaced structures. If we neglect soil structure interaction, that's equivalent to assuming the structure is supported on rigid materials. And you decide to neglect it, you are making that assumption. I can recognize now that the file that I opened up is not the one that I have made some modifications to. And I'm going to go to that file because there's an important aspect that I want to get across here. So I apologize for the delay. Go back. I modified it in the course of the review last week. So let's look at the effect that soil structure interaction can have on the demands that are placed on a structure. So let's look at a case where we have a soil with a fixed base natural period of T sub A. So this is case A, structure A. If we consider soil structure interaction effects, lengthening of the period goes from T sub A to T sub A tilde, will take us from this spectral acceleration level and a corresponding base shear down to a lower value here, because we're on the descending leg of the response spectrum. The increase in damping that occurs due to soil structure interaction will drop the spectral acceleration down a little bit more. And so what we see here is a beneficial effect of soil structure interaction. We've taken our design spectral acceleration from this level all the way down to this level. And so soil structure interaction here has decreased the demand on the structure. So the base shear that we would be designing for would be at this level instead of this level. So there's a beneficial effect when we are on the right side, to the right of the peak in our response spectrum. But if we look at case B, where we have a structure with a natural period T sub B that's less than the peak in our response spectrum, its fixed base spectral acceleration is at this level. If soil structure interaction lengthens that natural period from T sub B to T sub B tilde, that will bring us up this curve to a higher spectral acceleration. So that period lengthening is tending to increase the demands on our structure and increase the design base shear. But we also have an effect due to the increase in damping. And so if we account for the increase in damping, that tends to reduce the response. And so we drop down at the same period, T sub B tilde, to a higher damping response spectrum. And so the net effect in this case is to increase the amount of base shear So we see two competing effects here. The period lengthening is tending to increase it, the increased damping is tending to decrease it, depending on where we happen to be with our individual structure. One of them may be greater than the other. In this case, the period lengthening effect was greater than the damping effect, and we ended up with a higher base shear than the fixed base value. But there could be instances where, if we're starting up closer to the top here, where the slope of the response spectrum is not as large, the increase in base shear due to period lengthening is not very large, but the decrease due to damping is larger, and it will reduce our value. So soil structure interaction can either increase the demands on the structure or decrease the demands on the structure, depending on what the natural period of that structure is relative to the response spectrum that we're working with. So both things can happen. Okay, so we talked about these things. Let's talk now about soil-pile interaction. We have deep foundations. We usually have them because we have poor soil conditions. There may be verifiable conditions, but it may just be soft clays, like we may have in many areas here. We're going to bypass these soft, weak, compressible materials with deep foundations. If we use piles, we drive the piles into the ground, we vibrate them into the ground. If we have heavy loads, we're going to need to use multiple piles and connect them by a pile cap to resist the loads that are going to be applied. And we can have vertical loads, horizontal loads, and overturning loads being applied to these foundations. We may, in some cases, instead of driving piles, construct a drill shaft foundation. We'll auger a hole in the ground, put a rebar cage in, and fill it with concrete. So a pile group may look like this while it's being constructed. The pile cap has not been cast yet, but we can see that it's being cast inside of forms here, and there's a gap. You can see a little bridge across here for people to get in and out of this pile cap area. There's a gap between the soil and the edge of the footing. The pile cap is going to be constructed, so the excavation is a little more visible there. Eventually, this area is going to have to be filled in, and it can be difficult to compact soil in a narrow space like this. So we may have good compaction, or we may have poor compaction in instances like that, and that can have some effects that we'll talk about a little bit later. Or a drill shaft foundation. We can drill a large diameter hole in the ground, put in a rebar cage, fill it with concrete, and have a single foundation of a larger size that can resist and support heavy loads. If we look at a single pile or a single drill shaft, they apply vertical loads. They're resisted by skid resistance. It's mobilized along the sides of the foundation, and by tip resistance, the bearing pressure that develops on the base of the foundation. Skid resistance is usually high for fine-grained soils, like clays, and it's usually lower for sands. Tip resistance is the opposite. It's usually relatively low for clays, and it's higher in sands. Sometimes we'll have upward acting loads on these foundations. In that case, our skid resistance is going to provide resistance to uplift, and it's only going to act in one direction. It's going to act in the opposite direction. It'll be high for clays, it'll be low in sands. Tip resistance we won't have. We might temporarily have a little bit of suction, but we can't rely on it, and it wouldn't last very long anyway. So we have different behavior occurring under these conditions. We often want to measure the resistance to vertical loads so we can perform pile load tests. In pile load tests, we will have a hydraulic jack that's going to push the test pile downward. We may have a series of reaction piles surrounding it to provide the resistance to that downward acting force. We'll instrument the piles with a series of strain gauges. So if we notice if we measure the strain and we know this axial stiffness, we can calculate the load at any point along the pile. If we start to perform this pile load test, we apply usually a relatively small load at the top. We're going to be compressing the upper portion of the pile. It's going to be resisted by some compression or shearing of the soil adjacent to the pile, and we can measure that load as our strain gauges move down the pile. As we increase the load, we'll start to see the effect extending down to greater and greater depths, we generally can mobilize skin resistance at pretty small displacements, on the order of a centimeter or less, of pile displacement relative to the soil. The tip resistance requires more deformation, more pile tip movement in order to be mobilized, because we're mobilizing the strength of the soil in a pretty big zone underneath this pile or shaft. And so we don't mobilize much tip resistance in the early stages of this test, but as the test continues, we'll eventually fully mobilize all of the skin resistance, and our increasing capacity will come from mobilization of this tip resistance. And so we may have some ultimate resistance that's going to have a component due to the tip resistance and a component that's due to the skin resistance. They'll add up to our total pile capacity. If we keep track of the pile head displacements during that test, it'll look something like this. As we apply loads, the pile will deflect a little bit initially, but we start seeing nonlinear behavior, and eventually we reach a maximum capacity and we can't resist any more load than that. The pile just starts to plunge downward into the ground. So we have some initial stiffness, and that stiffness decreases as we get up to mobilizing the full capacity of the pile. We can try to characterize those with a tangent stiffness, like the little lines that I showed previously, or with a secant stiffness that just represents the average stiffness from the origin up to some displacement level. In both cases, those stiffnesses are going to decrease as the amount of pile displacement increases. So the soil is not linear and the pile capacity is not linear. We can perform lateral load tests on piles to examine their behavior. The behavior is complicated. In a horizontal plane at some depth below the ground surface, we'll see again initially with no lateral load, symmetric stresses being applied. But as we apply a lateral load, the stress field changes. We'll have some resultant force P that's mobilized with a displacement of the pile Y, and we have a PY curve that captures that aspect of the behavior. We'll be concerned about the stiffness and the strength. So we refer to that strength as the ultimate resistance, P ultimate. At a large depth, what we'll find is that the pile is just moving laterally with respect to the soil. The soil moves in a horizontal plane, and it's as though the soil is flowing around that plane. And there are solutions for that problem available to estimate what that ultimate resistance would be. At shallow depths, things are more complicated because the soil will tend to move upward in a passive wedge as it moves outward under the loading that's applied to a pile. And so it becomes more complicated, but we can calculate ultimate resistance and develop PY curves for this case as well. So if we apply loads, we'll be mobilizing this wedge in a fashion that looks like this. If our loads are cyclic, we'll mobilize the resistance of the soil and a wedge on the opposite side. Same resistance in both directions under level ground conditions, and symmetric loading will give us symmetric displacements. But if we have sloping ground conditions, now applying a lateral load in one direction may cause resistance to be provided by a very large wedge of soil in that direction. But when we reverse the load, we have only a small wedge of soil that's providing resistance to that load. And in this case, we're going to have a lot more resistance to pushing that pile in an uphill direction than in a downhill direction. And because of that, when we have symmetric loading, we're going to get response displacements that are not symmetric. They're going to tend to accumulate in the downslope direction. So we can perform lateral load tests. We put in pairs of strain gauges so that we can measure the curvature. On one side it will compress, the other side it will extend. If we make these measurements, we can measure the curvature. We can multiply that by the flexural stiffness to get the bending moment along the length of a pile. We can integrate that and get a shear force and get a lateral resistance from that, lateral soil resistance. So we're differentiating the moment diagram. We can take these curvatures and integrate them twice and get displacements, and that allows us to start building up a PY curve. And we can do this at different depths of our strain gauge pairs. And so this is the way we measure these PY behavior in the soil. People have done that for different soils, for sands, for clays, under static conditions and cyclic conditions. In soft clays, we see gaps forming, and the gap forms. We have this kind of unusual shape where there's no resistance as the pile is exposing the gap. And then when it makes contact with the side of the gap, the resistance starts to pick up again. So we have these kinds of behaviors that are published in the literature. It's easy to find these types of PY models. There's rate dependence that we have to consider. If we're in clayey soils, we have to recognize that there's a viscous component of resistance that usually provides about a 10% increase in the stiffness and strength of the soil for a 10-fold increase in the strain rate. So if we multiply the strain rate by a factor of 10, our stiffness will go up by about 10% or so. When we perform these loading tests in the field, we usually apply the loads quite slowly, and so we'll underestimate the kind of stiffnesses and resistances we can get in the field under earthquake loading conditions where the strain rates are going to be much higher. So we need to account for that. If we're looking at single pile, I showed this equation previously. I think I showed too many equations. We have near field and far field elements. We already talked about how we'll use the near field to describe the PY behavior. We use the far field elements to describe radiation damping, and we can do that well in the time domain. We will then discretize our pile, and we'll apply TZ curves to describe the axial load behavior. At the tip, we can put in a QZ curve that describes the development of end-bearing resistance. Skid resistance, as I said before, is usually mobilized at very low displacement levels. The tip resistance requires a lot more displacement in order to be mobilized. We have different types of loading, and so in a complete analysis, we will typically have PY curves to represent the lateral load resistance, TZ curves to represent the vertical load resistance, and a QZ curve at the base of the pile to represent the mobilization of end-bearing resistance. When we apply loads to a pile, the skin resistance is mobilized in a zone that's very close to the pile and is mobilized all along the length of the pile. The tip resistance is mobilized in a large zone underneath the pile. And so its vertical stiffness of this pile is going to be influenced by the entire soil profile. Lateral loading, when it's applied at the pile head, it's going to cause large deflections at the pile head, but they're going to decrease as we go down the length of the pile. So most of the resistance, as I said before, is going to be provided by the shallow soils near the ground surface. The deeper soils aren't going to participate much. They're not going to contribute much to the lateral resistance of loads applied up at the ground surface. There are procedures available for estimating, based on elasticity theory, the stiffness of a pile with respect to loads applied up at the head of the pile. So these are available for a uniform soil stiffness, where it doesn't change with depth, horizontal coefficients, rotational coefficients. They take the forms that are shown here based on elasticity. So we have the horizontal stiffness, the rotational stiffness, and then cross-coupling terms. Rocking and swaying are coupled in this instances, one affects the other. We have similar relationships that are available for a material whose stiffness increases linearly with depth, and for a soil whose stiffness increases quadratically with depth. So these are relatively straightforward problems, and solutions are available for those stiffnesses. If we have a more realistic, a layered, non-linear soil, we may have to go into a PY type of analysis in order to capture the individual signature or personality of that particular site. When we have ground shaping, with a uniform soil profile, we'll see relatively uniform deformations developing, and they're going to impose loading on our pile foundation. We have a flexible pile. Once again, it's going to move with the soil, high curvature but low bending moments. The flexural demands, though, are going to be high potentially all along the length of the pile, not just at the surface. pile head motion is going to be the same as the free field motion. If we have a stiff pile, it's not going to move in the same way as the soil moves. The curvatures will be lower, but the bending moments will be higher. The flexural demands are still going to be potentially high all along the length of the pile, and the pile head motion will be different than the free field motion. So if the pile is supporting our structure, we need to know what that pile motion is going to be. If we have a common situation where we have piles extending through soft soils into stiff soils, then things can become different, because our free field motion now will tend to have a kink in it at that interface between the stiff soil and the soft soil. And so there's a high free field curvature at that boundary that's going to induce high bending moments in the pile. And that leads to the kinds of damage that we've seen. In this case, in this particular case, the soil was soft because it liquefied, but if you have soft clays and piles extend through them into stiffer materials, you're going to have similar types of displacement patterns, and you have the potential for similar types of damage under equivalent shaping conditions. If you then have, say, a stiffer crust material, maybe some fill placed on top of the soft soil, then that fill can grab the top of the pile, and the stiff soil down at the bottom is going to be grabbing the pile so that it restrains rotation. And if it restrains rotation, and the soil in the middle is moving significantly like a soft clay will or a liquefiable soil, then you are really putting some high bending demands into your pile foundation, both at the bottom of the soft material and also up at the top. If that fill or that stiff clay or the stiff layer at the top, crust, is thick enough and competent enough to restrain rotation of the pile at the top. So we get high bending moments at both locations, and then we see these kinds of damages occurring where we fracture a pile in two places. So we have inertial loading that comes from the structure, and it produces high demands, high bending moments in the pile, the highest near the ground surface. We have kinematic loading, where the pile is loaded by movement of the soil, and that can be high at any point along the length of the pile. If we have lateral spreading, we're going to have high levels of bending moment induced both by the crust and by the impedance contrast down at the base. And we have to add the inertial loading to the kinematic loading to determine what our total demands on the pile are going to be. In some cases, it may be the inertial demand that dominates the response, and that controls what we need to design for. In other cases, if we add this inertial demand to the kinematic demand, we may still see that it's the kinematic demand that's controlled. So either one can control the peak bending moments in our pile and control the design of the pile. If we're looking at all forms of loading, we'll have all of these elements. Our PY curves will typically vary with depth, because the ultimate resistance is going to increase with depth. We apply some load, and we get some responsive resistant elements. If we have liquefiable soils, it's common to use estimated or computed pore pressures to soften the PY curves. And most of the available codes that will do this, or you can do it manually, will have you soften them in proportion to the amount of pore pressure that has developed. And so if you have pore pressures that reduce your effective stresses to 25% of the original values, you'll soften this down to have an ultimate resistance of 25% of the original resistance. So your PY curves become softened. But in a liquefiable soil, you have phase transformation behavior occurring in the vicinity of that pile. And so the actual PY behavior is going to be more complicated. And you'll see some stiffening occurring as the soil dilates in this region adjacent to the pile. Usually when we're using piles and we have significantly heavy structures, they're going to be constructed in pile groups. And when we apply lateral loads to a pile group, we can model it in the same way with PY, TZ, and QZ curves. A pile group, though, is going to behave differently, and that if we apply a load here, it's going to result in higher compressive loads on the piles on the far side, and it's going to reduce the compressive load on piles on the near side. And so we have the potential for bearing failure occurring here that we might not have otherwise. We might have the potential for pull-out of piles on this side. So lateral loading of a pile group is going to cause changes in axial loads on individual piles. They may go up and they may go down depending on how the pile is in the pile group. But those loads cycle back and forth, and so piles that are in compression, when the load's moving one way, they be an extension when the pile goes the other way. So we can use these types of models to predict the behavior of these groups. 3x3 group, 4x4 group. Our piles are usually spaced at 2.5 to 3 diameters from each other. We should recognize that when piles are loaded and pile group moves, the piles are going to be loading the soil adjacent to them, and there will be some zone of influence that each of these piles will be inducing in the soil. And if our piles are spaced closely together, they can overlap with each other. And so the piles are interacting with each other, and the capacity that we get from these 4 piles may be less than 4 times the capacity we would have from any one of those piles if it was tested by itself, or loaded by itself without any adjacent piles. So there could be an inefficiency in a pile group when they're closely spaced to each other. And all of these piles will cause movement of the soil and mobilize the strength of the soil, and they'll overlap with each other. So not all the piles in a pile group are going to provide the same resistance to the lateral load that's applied. So we have piles to soil to pile interaction that's going to affect the capacity and stiffness of a group. We can place the piles at very large diameters and they would act independently, but then we'd have very large spans in our pile group and our pile cap, and its cost would go up. And so we're typically in the range of 2.5 to 3 diameters, and we should recognize that there's going to be some interaction there. In load tests on instrumented piles, if we look at the leading row here, the row that's in contact with the soil on the other side of the load, we call that row 1. Row 2, we have trailing piles, leading pile, row piles, and trailing rows. What we'll find is that we'll get the highest loads being resisted by the leading row. So this is the results of some tests that were performed in the field. The results for a single pile are shown here, tested by itself without any other piles around. Here's the load per pile of the leading row and the next row, and then the trailing rows all resisted lower levels of load than the first and second rows would, and they're all lower than a single pile by itself would resist. So the leading row will take the greatest load. The trailing rows will take less load. The group effects are typically handled by P multipliers, where we account for the different levels of resistance that are provided by the different piles. We should recognize, though, under earthquake loading conditions, the row that's the leading row at one point in time is going to be the trailing row when the forces go back the other direction. And we have shaking in 2 directions. And so horizontal shaking in 2 directions. So the leading row, the pile group is going to be moving around in a 2-dimensional plane. There's going to be a leading row in the X direction, then the Y direction, then the other case, and the response becomes very complicated. What we find is that as we get more and more cycles being applied, the load distribution tends to even out, and these row effects tend to become smaller. Instrumented groups have been used to develop recommendations for group reduction factors, the P multipliers. We use the PY analysis, and they're showing this figure. The pile bending moments are also influenced by the position of the piles within a pile group. A single pile will have greater bending moments than the piles within a pile group. The leading row in a pile group will have the highest bending moments, and trailing rows will have lower bending moments, and after the third row, they tend to all be about the same. If we have an embedded pile cap, we can get a lot of resistance, a lot of stiffness from the size of the pile cap. We can start to develop passive resistance in the soils that are adjacent to the pile cap. And that can play a big role in determining the stiffness as well as the ultimate capacity of that pile group for lateral loads. However, we have to be sure that we have good contact between the soil and the sides of the pile cap. If that soil in an excavated zone is not well compacted, it's not going to provide much resistance. It's not going to provide much stiffness or much of a contribution to the stiffness. So it's an important consideration in determining what the stiffness of a foundation system is going to be to understand how it was constructed. If the concrete is cast directly against the soil, you'll have a good contact there. And you can rely on that to provide some stiffness and some strength. But if you don't have that, then it's not going to be as effective. So we have to pay attention to the way that soil was compacted, at the level of contact between the pile cap and the surrounding soil. For high overturning moments, we're going to have high demands in the axial direction on the outer rows of piles. We'll have high resistances under some of the piles, and we may have uplift occurring under other piles. If you have a very tall structure with a small foundation, if it's slender, you can have high uplift loads occurring. These can lead to yielding of the piles or movement bearing capacity failures of the soil. The piles will have some moment rotation behavior in flexure, and they will dissipate some energy as a result of that. That can be accounted for in some of the computer programs that we use to do these analyses. Dynamically, we often have to estimate the stiffness of foundations for analysis of the structure. There are impedance has two parts, elastic resistance and viscous resistance. They're out of phase with each other. We often model the dynamic stiffness using a stiffness multiplier that will multiply by the static stiffness. There are relationships available for estimating the static stiffnesses and the dynamic multipliers. Those dynamic multipliers that are illustrated here are often close enough to 1 that they're assumed to be equal to 1. So it's not uncommon to do that, but there are techniques available for making more accurate estimates and accounting for the dynamics if necessary. There are different ways that we can perform our analyses. I'm tempted to skip through this, but I'll go through it very quickly. It's in your notebooks. We can do a complete analysis of the entire, in this case, of the bridge, foundation, pile, soil system, calculate the entire response in our model. If we do this, we'll attach PY curves to all of our nodes. We'll attach TZ curves to all of the nodes. I'm not showing all of them here. We'll attach QZ curves to the tips of all of the piles. And we'll apply our loading to the ends of those elements. So we'll perform a pre-field site response analysis and calculate the loads, the calculated ground motions at every depth, and we'll apply those as our inputs here and measure the response. In some cases, we will choose to cut the model off, say at the mud line here, where the foundation enters the soil. We'll then represent everything below that, the piles and the surrounding soil, in a kinematic interaction analysis where we'll compute foundation input motions. There will be a horizontal motion, vertical motion, and rotational motions, and we'll just have a model of everything above the mud line. We'll then take those foundation input motions and apply them to the ends of these springs and calculate the response. And if we have a perfectly linear system, we'll get the same response. We may, under other circumstances, have a structural engineer that says, I only want to model the structure itself. And if that's the case, we'll have to perform an analysis, a kinematic analysis of our foundation system up to this point, calculate foundation input motions, and apply those to the ends of springs and dash plots that represent everything below that depth, and calculate the resulting response. So these kinds of substructure analyses will work well for linear systems. If we're going to apply it to a nonlinear system, we can use an equivalent linear approach and iteratively change the properties to be consistent with the levels of response that we see. And it can take some time to do that, but it makes an approximation to the nonlinear response. If we're going to truly measure the nonlinear response, we have to do a complete analysis of the entire soil structure foundation system. So in conclusion, to summarize, deep foundations are complicated. For buildings, we see that kinematic interactions affect foundation input motions, but inertial interaction effects are usually more important. For bridges and wharves, waterfront types of structures, kinematic interaction effects can often be very important. They can be the dominant factor in controlling our designs. Permanent deformations under these conditions can be quite important. We can still have important inertial interaction forces, but often the kinematic effects are the most important. When we're looking at inertial interaction, we really need to know the stiffness of our foundation system. That's what's most important. For single piles, it's coming from flexure. For pile groups, we have both flexural and axial loads that are controlling the stiffness and response of our system. If we have an embedded pile cap that has good compaction or good contact with the soil, it can provide a lot of stiffness to us. We often have to make approximations to the actual behavior. We do that in all aspects of geotechnical engineering. But we should recognize that we're making those approximations. Structural engineers are making approximations as well, and it's important for the geotechnical and structural engineers to be talking to each other about any kind of evaluation of soil structure interaction. So thank you. There are a number of references that could be useful to you that I referred to in the presentation and they're listed here. Okay? Going to lunch now. We'll meet up and start up again at 13:50. Ask a question.
Потом тогда ну так тесты туда можно. Bueno.